Good afternoon and welcome. My name is Alan Middleton. I'm chair of the Department of Physics, and it's my great pleasure to welcome you here today to celebrate the induction of Duncan Brown as the inaugural Charles Brightman Professor of Physics. This is an exciting occasion for us to recognize Duncan Brown's accomplishments in education and research, and to acknowledge the generosity of the gift that established the Brightman Professorship. Speaking of Brightman, I would like to see, where is Josh? Josh Goldberg is, there's Josh. Josh is the one person I believe in this room who actually was in this building when Brightman was here. You were a student here at the time. And I guess you could speak to Josh at the reception afterwards if you like. But in any case, I am grateful that there are so many people here to participate in this celebration. We have our students, faculty members, staff members, postdocs from our department. We're honored to have the College Board of Visitors in attendance. I wish to also welcome the members of the administration and the college and the university, Dean Ruhlandt, Provost Wheatley, Chancellor Syverud, to our department. And I would like to invite Karin up to speak about faculty recognition.
It's a true pleasure to be here. This is really an exciting afternoon. And so thank you, Alan. And at this time, I'm inviting Professor Duncan Brown to join me in front of the room. So today is very, very special. We're celebrating Duncan Brown, a world-renowned expert in gravitational-wave astronomy and astrophysics. Just as Charles Brightman was an avid teacher and researcher, Duncan Brown has epitomized the tenacious entrepreneurial spirit of our physics faculty. Today, we recognize Duncan for his research accomplishments, specifically the leadership role he has played in the historic detection of gravitational waves involving the Laser Interferometer Gravitational Wave Observatory. I managed to say it. Or LIGO. We also recognize his excellence in teaching, mentoring, and writing, as well as his contribution to campus research computing. Duncan did one other thing, and that is engaging in outreach to provide research opportunities for underrepresented STEM students. So Duncan has done many things, and we're really proud of you, and we're really excited to be here with you and celebrate you. As the Brightman Endowed Professor, Duncan will push gravitational wave astronomy and nuclear astrophysics in bold new directions. Vice Chancellor Wheatley, would you please come to the podium?
Thank you, Dean Ruhlandt. I am delighted to be a part of this ceremony recognizing the inaugural Charles Brightman Endowed Professor of Physics. Today, we honor Duncan Brown for his excellence as a teacher, a mentor, a collaborator, and a world-class scholar. He truly embodies the passion for excellence and commitment to discovery and learning that are the hallmarks of truly outstanding faculty across the disciplines. And he speaks to the critical importance of endowed chairs and professorships to building and sustaining academic excellence at Syracuse University. Endowed chairs and professorships not only confer peer recognition on a faculty member for exemplary scholarship, they empower the dean to attract, recruit, and retain outstanding faculty who are both world-class teachers and researchers. They help us compete successfully for the brightest, most talented students and for top-notch faculty who want to work alongside the best. They simultaneously affirm and honor distinguished faculty for their scholarly achievements and motivate rising faculty stars to greater levels of achievement. In short, Endowed chairs and professorships are crucial to our capacity to fulfill our academic mission. I am grateful to those donors who have the vision and desire to establish such a powerful and significant gift, and I am most appreciative of the opportunity they give us all to publicly honor outstanding and innovative scholars like Duncan Brown, whose passion for discovery advances knowledge, inspires students, and enhances our standing as a world-class research university. I would now like to invite Dean Ruhlandt and Professor Duncan Brown to join me at the podium for the presentation of the medallion. Oh, okay. So, on behalf of Syracuse University and the Board of Trustees, it is my great pleasure to induct you, Duncan Brown, as the inaugural Charles Brightman Professor of Physics in the College of Arts and Sciences. And now it is my privilege to invite Chancellor Kent Syverud to say a few words.
Thank you, Michele. Welcome, everybody, to a great department in a great college. This department has an extraordinary history, and I've discovered physicists have an extraordinary sense of time and history. And so I should first say at this major university event that I want to acknowledge the Onondaga Nation, the people whose on ancestral lands the university sits. I also want to talk a little bit about timelessness in connection with Duncan, because my wife, Ruth Chen, and I, at each time when someone is put in a new endowed chair, we present that person with a personal gift, not from the university, but from us. And we try to do something that shows the timelessness of great scholarship and great scholars. So much of what we do at a university is or seems ephemeral. As anybody who's taught a class knows, it can sometimes seem like everything's forgotten the next time you come in the room. Endowed chairs are the opposite of ephemeral. They last a long time. They celebrate in scholarship and teaching that lasts a long time. And often that will outlive all of us, as Charles Brightman's legacy has outlived him by many decades. So to mark this, what we do is we select and we purchase a rare book to give to the chairholder to emphasize that fine scholarship, like endowed chairs, is timeless and endures. Finding the right timeless book for Duncan Brown, think about it, was a bit of a challenge. His scholarship in some ways, your scholarship in some ways challenges our understanding of time and space. It took several months. We got help, as usual, from our extraordinary Dean of Libraries and University Librarian David Steetman, and wonderful people and professionals in the library, and from Professor Peter Salson, who gave us advice on books in the field. And we settled on this one in a beautiful box created by our Special Collections Department in the library. I think I've got that right. Do I have that right? This is a first edition of Arthur Stanley Eddington's Space, Time, and Gravitation, an outline of general relativity theory. This was published by Cambridge University Press just about a century ago. Eddington, for those of you who are not physicists, I will say, was an English astrophysicist, early part of the 20th century, contemporary of Charles Brightman, and one of the first proponents of Einstein's theory of relativity. He was secretary of the Royal Astronomical Society during World War I. He was among the very first to receive word of Einstein's theory, and in 1919, his observations and photographs taken during a solar eclipse would be hailed at the time as significant confirmation of the theory of relativity. He was also incredibly witty and entertaining as a writer and lecturer. Does that sound like someone you know? And he wrote this book to give an account of the theory that would be approachable to others, not in the field. And so, in particularly others without the mathematics and physics and philosophical training that most required at the time to approach the theory of relativity. And it's witty and clear and really helped build public awareness of the general theory of relativity in the English-speaking world. So it seemed like a good match for Duncan Brown for reasons you've already heard. And so we are so fortunate to have Duncan here and this department here. So Ruth and I, in honor of your appointment as the inaugural Charles Brightman Professor of Physics, present you space, time, and gravitation. So.
Let me just first of all say that I'm honored and humbled at the appointment as the inaugural Charles Brightman Professor of Physics. This is a great honor for me and for the Gravitational-Wave group at Syracuse University. Are a fantastic group of people who I've had the pleasure of working with, some of the best students and research scientists in the collaboration who've gone on to fantastic careers in the wider field. I'd like to thank the Chancellor and Dr. Chen for their kind words and their generosity and their wonderful gift. My first slide is actually connected to something you said about the lensing, Eddington's lensing mission, so I will refer to that in a minute. I'd like to thank the Provost and Dean Ruhlandt for their support. I'd like to thank Alan for being a fantastic department chair when one of his faculty members went missing for about 6 months and stopped responding to emails while we discovered gravitational waves. I'd like to, of course, thank Peter Solson, who's been an absolutely wonderful mentor to me for the last 10 years. He's been one of the, he's a kind, generous, wonderful scientist, and he's been a good friend to me over the last 10 years, and I owe a lot of where I am now to him. I'd like to thank my wife, Emily, and my daughter Zoe for being very patient with me and all their love and support over many years and many years going towards the future. And I'd like to thank the College Board of Visitors for being here and showing their support and active engagement in the university and their deep and ongoing support for the college. And of course, I'd like to thank the Brightman family for their generosity in establishing this position and allowing me to move forwards with my research. My appointment as the Brightman Chair reflects the best qualities of Syracuse University, both in research and teaching. This is a university that prides itself on academic excellence in research and teaching. It's a wonderful place. I'm very happy here, and I'm glad that I've had the support of the university at all levels, from the administration through to the undergraduate students here are fantastic, working on research projects and have enabled us to make this wonderful discovery. So thank you to everybody. Okay, so that said, I will switch to my more normal mode of speaking and tell you about the discovery of gravitational waves. So let me begin by explaining what's seen here. So this, Chancellor Syverud mentioned that one of the first early tests of Einstein's theory of relativity was the detection of the bending of light by the sun. In relativity, matter tells space how to curve, and space tells matter how to move. That's relativity in 2 sentences. I'll explain that in a minute. The theory of relativity really upended our knowledge of the way gravity works. Gravity is, in some sense, the most ubiquitous force in our life. It's the force you feel if you drop something, but it's also the least understood of the fundamental forces of physics. And so we've tried for many, many years, going back to Newton, and then the great leap forward of Einstein, to understand the theory of gravity, to really understand the nature of one of the fundamental forces that is so important. If it wasn't for gravity, we wouldn't be here. We'd just be a cloud of hydrogen gas in the universe. Gravity brings that hydrogen together, forms stars. Those stars burn hydrogen to heavier elements, and those heavier elements eventually become us. But later on in those stars' lives, those stars exhaust their nuclear fuel, and if they're heavy enough, gravity will take over again, and gravity will pull those stars down and collapse them down into smaller and smaller objects. And if the star is big enough, the gravitational pull is strong enough, then that star will actually collapse down. Nothing can stop that collapse, and that star will shrink down, collapse down to a black hole, a region of space where nothing can escape. No light can escape, no information can escape from that black hole. So what's shown here is a computer simulation of what it might look like frozen in time if you were near two black holes. So here's one black hole right here, here's a second black hole here. And what you can see simulated in the background is a field of stars. And this distorted pattern around here is the extreme gravitational lensing, the bending of the starlight around the massive gravity of these black holes. These black holes warp space-time, and they bend the light from the stars behind them. Eddington saw this very, very subtle effect grazing around the sun, but this is a very extreme effect of what it would look like if you were close to these two black holes. Another effect is that things don't stay still in the universe for very long. Things move around. The universe is a very dynamic place. And these black holes actually orbit around each other. Just like the Earth orbits around the sun, these two black holes orbit around each other. And as they orbit around each other, they create ripples in the fabric of space-time that propagate out at the speed of light, carrying the information about what's happening with these black holes. Now these waves, these gravitational waves, these ripples in space-time that propagate outwards carry energy away from the system. They take energy away from the system, so the two holes get closer and closer together until eventually they collide into a single hole that settles down as a final state of these two stars merging. So these stars live lives of, the universe is about 14.5 billion years old. These stars live 10 billion year lives, burning their nuclear, forming from clouds of hydrogen, burning their nuclear fuel, collapsing down to form black holes in this binary system, eventually colliding into each other and settling down to this final black hole. So this is a prediction of Albert Einstein just over 100 years ago. Einstein, after he wrote down the theory of general relativity, he very quickly realized that there were some dramatic consequences. He realized that there were ripples in space-time that carried the information about changing gravitational fields of the universe. In Newton's theory, there's action at a distance. If I change the gravitational field over here, then the entire universe realizes instantaneously. But Einstein said that information propagates at the speed of light, and so if I change the gravitational field over here, then it takes a finite amount of time for that information to reach the distant corners of the universe. And that carrying that information is these gravitational waves. So Einstein predicted the existence of gravitational waves just over 100 years ago. It's one of the first predictions after general relativity. Roy Kerr, who was a postdoc here at Syracuse University in the gravitational physics group at Syracuse University, working with Josh Goldberg collaborators, Roy Kerr wrote down the solution to Einstein equations that describes the astrophysical black holes of nature. Roy Kerr wrote down what's called the Kerr metric, which describes what happens when a star that's rotating collapses down to form a rotating black hole. So this black hole is described by the mass that's in the black hole and how fast it's turning around. So with these two pieces, with the prediction of gravitational waves and with the mathematics that describes the black holes we expect to see in the universe, there began a 50-year quest both to understand relativistic astrophysics, to understand the nature of these black holes, and then after a conference in 1957 where there are a lot of arguments about did these gravitational waves exist, were they just an artifact of the theory, just some coordinate transformation of the theory, and they weren't really a physical wave. After 1957, people realized that they did exist, you could detect them, and people started then another 50-year quest to go out and try and build machines that could actually detect these ripples in the fabric of space-time produced when two black holes collide into each other at about a third the speed of light. So this is what our picture of gravity. So in Einstein's theory of gravity, we think of space-time kind of like the surface of a trampoline or maybe the surface of a pond. When you put mass on here, it curves space. So gravity is described as curvature in space-time in Einstein's picture. So this is what I mean by matter tells space how to curve. So here's a massive object, less massive object, and a light object producing different amounts of curvature. And a black hole produces so much curvature that once you fall down this well, you reach a point of no return called the event horizon where no information can ever come back. So all the information about those stars disappears down that event horizon, leaving behind these black holes in space-time. And that's what we went looking for. When these two objects orbit around each other, here I've shown neutron stars instead of black holes. When two compact objects orbit around each other, if you stick your finger in a pond and you wiggle your finger around, you'll make ripples on the surface of the pond. And those ripples propagate outwards, and they move out to the edges of the pond. And these ripples carry the information about you wiggling your finger around in the pond. Gravitational waves carry this information about the two objects going round and round each other and eventually crashing into each other. So what we do is, we are many, many, many light years away from what's going on here. What we do is we look at the surface of the pond, and we look for ripples in the surface of the pond. And what we do is imagine putting two corks on a pond, and as the ripples go past, those corks will bob backwards and forwards. And so even if you couldn't see the water in the pond, you would see the ripples by seeing the corks on the pond bob backwards and forwards. And that's a way that we can find these tiny, tiny ripples in the fabric of space-time by looking at their effect on the rulers that we put down on space-time, like these little corks that bob backwards and forwards and tell us that the ripples are there. So how easy is it to find these ripples in space-time, these gravitational waves? Well, the answer is it's very, very hard. The physical effect of a gravitational wave, these ripples in space, is to stretch and squeeze things. So if you had a huge gravitational wave going through the Earth, then this would be the effect on the Earth. So as the gravitational wave passes through the Earth, it would stretch and squeeze the planet. As the gravitational waves reach higher and higher amplitudes, as the black holes merge, you would see this rippling effect on the Earth. Now, if we had a black hole system very, very close to our solar system, then this is what we'd see. Gravitational waves would be easy to detect. We would be very unhappy if the Earth was doing this, but the detection of gravitational waves would be an easy problem. But these black holes, fortunately for us, are fairly rare in the universe, so they collide into each other many millions of light years away from our solar system, and by the time these waves get to us, by the time these waves reach us on the Earth, they are tiny. You see the slightly faint text here, scale of effect vastly exaggerated. How vastly exaggerated? Well, the change in length divided by the length. So if I have a length and I think about a little change in length caused by gravitational waves, the actual change in length caused by a gravitational wave is 0.0000000, so 10 to the minus 21, a strain of about 10 to the minus 21. So over a distance of 4 kilometers, let's say, that change in length is smaller than the size of a proton. So over about 2.5 miles, you're looking for a change in length that's smaller than the size of a proton. And just to give you another way of looking at this in terms of astronomical scales, measuring strains of 10 to the minus 21, measuring these gravitational waves, is equivalent to measuring the distance between the Earth and the nearest star to the Sun, Proxima Centauri. That's a distance of about 4.2 light years. So measuring a strain of 10 to the minus 21, detecting these gravitational waves, is equivalent to measuring that distance, 4.2 light years, to about 1/10 the width of a human hair. So that's the scale of measurement, that's the scale of technological challenge that we need to overcome in order to detect these ripples in space-time. And that's why it took 100 years from Einstein writing down the field equations of general relativity, predicting the existence of gravitational waves, to actually discover these waves. It's taken many, many people many, many years. I'm part of a 1,000-member collaboration called the LIGO Scientific Collaboration that is big science. And it's big science because you can see us on Google Maps from space. So this is the LIGO Observatory. This is a device for measuring ripples in the fabric of space-time. What you have is a corner station here and 2 mirrors at the end. You shine a laser beam between them, and you measure distances smaller than the size of a proton over 2.5 miles. We have another one of these in Livingston, Louisiana. This is the detector in Hanford, Washington. We have another one in Livingston, Louisiana. And how they work is in that corner station, there's a laser. You shine that laser at a beam splitter, so half of the laser light goes in one direction, half of the laser light comes in another direction. It recombines at the beam splitter, and the light at the output, where we put a photodetector, fluctuates as these mirrors ripple backwards and forwards. Again, scale vastly exaggerated here. These mirrors are actually wiggling backwards and forwards a distance that is smaller than the atoms that the mirrors are made of. So there's a huge technological challenge I started working in gravitational wave detection in 1999 when I started graduate school. When I started graduate school, the first generation detectors, the first generation LIGO detectors had just been built. And it wasn't until my current generation of graduate students started graduate school that we got detectors that were sensitive enough to actually reach a level where we could detect these gravitational waves. This is what they look like. These are the mirrors. So rather than that little cartoon, this is the mirror right here that detects gravitational waves. This complicated system is to isolate those mirrors from the surroundings. And for the technical diagram is shown like this. This is something called a sensitivity curve. The bane of LIGO's life is noise. Noise from atoms jiggling around, noise from seismic motion, noise from the quantum nature of light itself, the fact that light comes in packets called photons. And all these noise sources add up that different gravitational wave frequencies, we have different amounts of noise where more noise is bad and less noise is good. So we're actually most sensitive, the noise is smallest here, in a frequency regime from about 30 hertz to about a kilohertz, which is also the frequency sensitivity of roughly the frequency sensitivity of the human ear, which is wonderful because it means you can actually plug a speaker into the back of LIGO and listen to the gravitational waves that the universe is producing. So, as I said, the initial LIGO detectors that were kind of my graduate career are shown in white up here. So remember, this is frequency on the x-axis, noisiness on the y-axis. More noise is bad. We want less noise, more sensitivity. And so this is where kind of I left things off, my first generation of graduate students. Where we turned on the advanced LIGO detectors last fall, we turned on the advanced LIGO detectors with much better sensitivity. So you can see that we have lower noise all the way across the band down here, and so we had much more sensitive detectors last fall. This is worth commenting on. This is where we think we can get these detectors after we've tuned them up. Building a gravitational wave detector is like building a car yourself and then tuning it. When you first build it, turn it on, it kind of vibrates, jiggles around, knocks around, there's noise sources. As you tune the detector up, the noise gets less and less, and so we still have this to play with going forwards into the future, finding new signals. So where we were last September is Stefan Barmer, a colleague of mine who's currently up at the LIGO Hanford Observatory, improving this noise for our data taking this fall. Stefan was up at Hanford and said, okay, I'm done commissioning, let's just leave it alone, let's just take some data and see what happens. And so they all went home late at night, they left the detector running, and then early in the morning, this happened. So what this shows, what you can hear, so I played this twice, once at its natural speed, which is a low frequency, and then once sped up, so it shifts a little bit more towards the range of the human ear. That rumbling you can hear, that low rumbling is the noise. That's what we're trying to get rid of in the detectors. That's what limits our ability to detect gravitational waves. At the end, you heard a little whoop, whoop. That's the sound the universe makes when it slams two black holes into each other at a third the speed of light. So that little whoop at the end is this signal right here. These two, you can see clearly these pulses. This is noise back here. You can see clearly these pulses, and then this pulse of gravitational wave power in what we call a time frequency plane, increasing in amplitude and frequency and making this little whoop chirp noise. And so 100 years of physics, of engineering, of discovery has led us to this beautiful signal here at the end where we thought maybe we'll see something that we'll have to tease out the data very, very carefully. The universe, the day we turned the detector on, gave us a gift, gave us a signal that's so loud and clear and crisp that you can see it and hear it in the data. So for the first time in human history, we can hear the sounds of the universe. We've been looking at the universe with telescopes for many, many years. We can now hear the sounds of the universe by plugging speakers into the back of the LIGO detectors and listening to the ripples in space-time as black holes collide into one another. So this is the GW150914 signal, so-called because it happened on September 14th, 2015. The signal first hit, these signals travel at the speed of light. It first hit the Livingston detector, and then 7 milliseconds later hit the Hanford detector. And by looking at the data, just some very, very simple looking at the data, you can actually deduce that this has to be binary black holes. Two black holes colliding into each other are the only thing that could produce this signal. Over about a fifth of a second, the signal increases in frequency and amplitude from 35 hertz to about 150 hertz as the black holes make their final stages of merger and collide into each other. And the only objects in the universe that we know of that can do that are two black holes crashing into each other. So this wasn't just the first discovery of gravitational waves, it was the first direct detection of black holes. So it made worldwide news. This is a collection from Stuart Anderson of the international newspapers the day after discovery, the New York Times here, and then papers from all over the world, from England, from Germany, from many, many countries, celebrating this wonderful discovery. Syracuse got a fair amount of press for this. This is one of my former Astronomy 101 students called me up and said, hey, I work for CBS News now. I remember you talking about LIGO in Astronomy 101. How'd you like to be on TV with Michio Kaku this afternoon? So, okay. Who's Michio Kaku? Oh, that guy. Okay. So, this is Sam, one of our undergrads. This is Shomi, one of our graduate students who worked on Discovery. Peter, we're on NPR. Fabian is a graduate student here now who comes from California. He was featured in the Orange County Register. And so this is the ripple that was heard around the world, this new discovery, this new way of looking at the universe with gravitational waves. So where do we go from here? We've made the first direct detection of gravitational waves. We've discovered two black holes colliding each other. We've built machines that are sensitive enough to detect ripples in the fabric of space itself. So where do we go from here? Where we go from here is the beginning of an entirely new kind of astronomy. Gravitational wave astronomy, gravitational wave astrophysics. We have a new tool for looking at the universe. We can look at that wave and we can say, do some back of the envelope calculations and say very quickly, oh, that must be a binary black hole. But can we go further than that? And we can. When we bring computer simulations, very powerful computer simulations of black holes colliding each other, solving Einstein's equations for two black holes colliding into each other, we compare them against the signals that LIGO detects, we can understand the nature of gravity itself. So this is a computer simulation right here where the input to this computer simulation was guided by LIGO's discovery. So by measuring the properties of those black holes, we fed that back into a computer simulation to tell us what the black holes looked like as they were inspiraling and merging into each other. So at the top, it shows what the black holes would look like if you could see them, the event horizon. These throats here are the curvature of space-time as these two black holes orbit around each other. And the trace at the bottom shows the gravitational waves that were produced in this merger as the black holes collide into each other and collide together. So we saw the last fraction of the signal. So we saw this. So it's slowing down. So we saw these two black holes spinning around each other, producing extreme curvatures in the fabric of space-time until they eventually get close enough to touch, form a single black hole that rings down as if you'd hit a jelly and forms and settles into a quiescent black hole at the end. And this waveform might look simple, but encoded in this waveform is a tremendous amount of information about the nature of those black holes, how fast they're spinning, how far away they are, what their masses are, the stars that form them, the processes that, the astrophysical processes that generate those gravitational waves. So this is an entirely new field of astronomy we can use to study the universe and study gravity. We made a detection on the first day of what we called the science run. The science run itself lasted from September 12th to January 19, 2016. So we actually took about 3 months of data. And the signal was so loud and clear that we within the collaboration were all convinced that it was true. Such a loud, clear, beautiful signal, we're all convinced that it was true. But it sure is nice to have a second one. And that's what we got. So when we looked at the result of the run, this is how loud our gravitational wave signals are. This is how many things we see. And these traces here show the signals produced by noise in our detectors. And then the blue squares here are the things that are not noise in the detectors. So signals, discoveries of astrophysical sources of gravitational waves. This is GW 150914 right here. This is the very loud event that we saw on the first day of the run. We also saw another very loud signal right here that stands up way above the noise. And then a third candidate signal right here, which wasn't loud enough on its own to claim as a detection, but I certainly believe is real, and we've seen a third signal. So we have two very clear, convincing detections of gravitational waves from merging black holes, and then a third signal that I think most of them in the collaboration are convinced are real. So these are the three signals right here. These are the gravitational waves of the signals. This is the first one we discovered, GW 150914. This is the candidate signal, the second one we discovered, and this is the third signal we discovered. And you can see that these gravitational waveforms look quite different. And so encoded in these, the amplitude, the way the waves evolve, the way they die off, the way they ramp up, this is where all that astrophysical information is encoded about the nature of gravity and about the binary black holes. So we have 3 detections. We're going to turn back on this fall, and the plan is to make more detections this fall with a more sensitive instrument as we go forwards. Who are the people who are going to work on this? Well, this is a picture taken last year. This is the Syracuse University Gravitational Wave Group. As I said, it's a fantastic bunch of people, undergraduate students, graduate students, research scientists, who all work incredibly hard. We're all incredibly passionate about the discoveries that we're making, about this new field of astronomy that we're opening up. It's a wonderful team to work with, as well as our wider team within the LIGO Scientific Collaboration. Here are some pictures showing the moment of discovery. So this is our group meeting area. This is Peter here and Sam, one of our undergraduates. So Sam, the Syracuse undergrad, actually ran the analysis that demonstrated for the first time that these signals were real. Chris Beer, a Syracuse graduate student, was heavily involved in writing that analysis. Many other people in the room, Shomi, Steve, and other people contributed to running this analysis, staying up very, very late to get these computer programs run. And this was the moment of discovery where we finally pushed a button that made all the graphs readable to the world readable to the collaboration on the internet. And this is a picture of Ray Weiss right here, who will hopefully win the Nobel Prize next year, the founder of our field, looking at this plot for the first time that was made by a Syracuse University undergraduate student with help from her colleagues in the graduate program here. So this is a wonderful moment of seeing Ray's face when he realized that his life work had come to fruition. This is Amber Lennon. Amber helped make the second discovery. She's another Syracuse undergraduate who was heavily involved in this research. She's now a graduate student at West Virginia University. So she is continuing to work on her gravitational wave studies there. This is the summary of the run, 3 detections made. These are all the binary black holes that we've seen. We've seen more binary black holes in the last year than people have seen in X-ray measurements over the last 20 years. We have this whole family of binary black holes that we're accumulating, discovering more and more about the universe, going forwards with this new field of astronomy, looking at where the matter that we see in the universe comes from. We actually, one thing that I don't have time to talk about, but I'll mention just briefly, is that we don't know where the gold and platinum in the universe comes from. We know that gold and platinum exists because we have it, we often wear it, but we don't know where the gold and platinum in the universe comes from. That's actually a current mystery in physics. We don't know where that material comes from. It's not made in supernova explosions. Supernova don't make enough of it. So there's actually an open question as to where this material that we have in this room comes from. And it could be produced in gravitational wave events as neutron stars collide into each other. And so when we see those ripples in space-time from binary neutron stars, from massive compact objects colliding into each other, they can spew out heavy neutron-rich material that can coalesce into the heavy elements like gold and platinum, which get recycled into the universe, into future generations of stars, and can populate our galaxy with these heavy elements that we see today. So this is the type of exciting physics that we're just at the beginning of. We're just at the beginning of an entirely new field of astronomy. And I'm very proud to be standing here today as the inaugural Charles Brightman Professor of Physics. And I'm very, very pleased to thank Syracuse University for the tremendous support that they've given gravitational wave discovery, the physics department, and our group in the college. This has been an absolutely wonderful experience, and I will stop there and take any questions. Thank you.
Thanks, Duncan. That was fabulous. Are there any questions?
I've never taken a physics course in my life, but I am interested in this, and I'm wondering, do I understand it correctly that in order to make a black hole, there need to be 2 stars going around each other?
So a single star can make a black hole, but in fact, most stars in the universe are in binary systems. So if you've ever watched Star Wars, you see Luke's home planet at the beginning of Star Wars, and you see the two suns over the horizon. So Luke's home planet is on a system that's a binary star system. Most stars in the universe actually have a companion star, and they orbit around each other. So most stars have a companion star, and the two stars orbit around, evolving together and evolving through their lives together. A single star, when a star maybe about 10 times the mass of the sun, so a star more massive than the sun, it burns very, very hot and bright. So it burns its hydrogen into helium, it burns its nuclear fuel extremely hot and extremely bright. And what stops the star collapsing down is that heat that's produced in the nuclear fusion. But when that source of energy, when that fusion fuel is exhausted, the universe fuels a star at the beginning of its life with a certain amount of hydrogen. And when that hydrogen is all burnt away, and when that hydrogen is burnt into heavier and heavier elements, and there's nothing left to burn, then the core of that star can no longer produce heat that pushes outwards and stops the collapse of gravity. And so then gravity wins, and that star collapses down into a black hole in a massive explosion called a supernova explosion, leaving a black hole in the middle. So single stars can form black holes, but in order to detect the gravitational waves from these black holes, we need them to be orbiting around each other, because it's that orbiting motion that produces the ripples in space-time that we detect with LIGO. So with the final black hole that's perturbed, that rings down like a bell, we can see the gravitational waves from that, but very quickly it settles down to a single black hole that just sits there for eternity doing nothing.
Duncan, can you talk a little bit more about the process of the listening? I mean, was it just fortuitous that the group was listening that night, or are they listening all the time, all the groups that are doing this around the world?
So the way we operate the detector is we have what we call observing runs. So because when we turn the detector on, it's not at its design sensitivity. It's not working 100%. So what we do is we interleave periods of making the detector better with periods where we leave the detector alone and use it to observe the universe. And what happened in last September is we'd scheduled an observing run to begin in mid-September. So we'd said, okay, enough messing with the detector. We're just going to leave it alone, and we're going to see what happens. We're going to see what it can see. It's listening to the universe. So what can it hear from the universe coming in on that detector? And there was actually a big debate between Ray on one side, who wanted to keep doing some commissioning, and Stefan on the other side, who just said, just leave it alone, just take some data. And in the end, we just decided, we're supposed to be in an engineering phase. The detector's calibrated. We'll turn it on. We'll take data. Once we're in that mode, all the data is recorded. So everything we record goes on disk. We can go back for all time for all the detector data was recorded when we're in observing mode. And so we plan these observing periods, and if the gravitational waves pass through the Earth in these observing periods, we'll see them. It's entirely probable that 3 gravitational wave events from binary black holes have passed through the Earth at a sensitivity that LIGO could detect over the last 6 months, but we haven't seen them because the detector's been down for upgrades. And so while the detector's down for upgrades, we're not sensitive, but this fall we're turning the detectors back on. It's actually scheduled to start in an engineering phase next month and then observing run in November. When we turn the detectors back on, they'll be 50% more sensitive than they were last year. 50% more sensitive translates to about a factor of 2 in the event rate, because that goes as the volume that we can see. So when we turn the detectors back on this fall, instead of seeing 1 signal a month, we expect to see about 2 signals a month. And we expect to start seeing new sources like binary neutron stars that we haven't seen yet. So the plan is to eventually get to a stage where we're at the best sensitivity we can get, and then we'll turn the detectors on and be listening all the time.
I understand there's the possibility of putting a LIGO in space, which would have more precision and accuracy. What's the status of that proposal?
Yeah, so that's a proposal called the Laser Interferometer Space Antenna. Before I give you the status, let me just explain what that is. So we've been using light electromagnetic waves to observe the universe since humans first looked up at the sky and saw the stars. And optical telescopes that our eye can see are sensitive to a very narrow frequency of the electromagnetic spectrum. You may have seen, I'll use my pop culture movie references again. You may have seen GoldenEye, the James Bond movie, with the giant Arecibo radio telescope. That's a radio telescope that looks for very low frequency sensitivity, very low frequency radio waves from the remnants of supernova explosions. At the other end, we have gamma ray telescopes that look for very high energy bursts of light that fly above the Earth's atmosphere. LIGO is kind of like LIGO is at the high frequency end of the gravitational wave spectrum. The LISA detector is a proposal to look at the middle of the gravitational wave spectrum at lower frequencies. And it has to be in space because LIGO sensitivity is limited by seismic noise, by ground motion. So if you want to go to lower frequencies, you need to get off the Earth and go into space. So that's what LISA is. LISA has received top marks from the National Science Board, the NASA Decadal Review for the last several reviews. The science payoff is tremendous. It also comes with a $2 billion price tag, which is very expensive. And but I believe that things are moving forwards with NASA, and there's been strong recommendations to NASA that NASA, I understand, are very sympathetic to. Now that LIGO has discovered gravitational waves, shown that gravitational waves exist, and we can do gravitational wave astronomy, to move forward with LISA with that space-based telescope. There are also ongoing projects at the very low frequency end with pulsar timing to detect very low frequency gravitational waves from extremely massive black holes in the cores of galaxies as galaxies collide. So this is a field that's at its very beginning, where we've only just made a few discoveries with one end. We have this whole spectrum to explore and a whole palette of discoveries out there waiting to happen.
Thank you, Duncan, and congratulations.